and stuff, but I want to take it up a step higher. This isn't on the test, of course, but I think you're all mostly bright enough you could follow along, and I think it'll help you see like some of these ideas. So like, we gave definitions of temperature, right?
Mm-hmm.
What was our first definition of temperature?
Agitation of molecules.
Okay, right, the random kinetic energy of molecules.
Mm-hmm.
Or in grade school, you learned how hot something was, right? That was temperature. And then I told you it was something else. Didn't I tell you what temperature really was?
Mm-hmm.
Yeah, you said 1 over T is equal to
The derivative of entropy with respect to energy. But how is that possible? Where did that come from?
Mm-hmm.
So I want to show you where that comes from. And how did they get entropy as a log of the multiplicity? So I want to show you these high level ideas and see how they work out. Okay, does that make sense?
Awesome.
Are you just showing us, or are we gonna have to?
I'm just showing you. You don't have to apply it. When you take thermal, you'll have to apply it. That's later. But not only that, I want to show you this, but it shows you a way to think about the universe. Right? We're so used to thinking of the universe like, not universe out of space, but like the world we live in, being described by the things we see, but a better description is the mathematics and the physics of the universe. Does that make any sense? And this is showing you an example, because this isn't necessarily something you see, but when you see the mathematics, it's really cool. So that's the idea. So we're going to talk about, okay, what is thermal equilibrium? Let's start with that. Come on.
all the particles in the same
Temperature.
energy.
Okay, they have the same random energy, the same average kinetic energy, right? So I've got two systems, a red system and a blue system. The red system you can see is, let me pull up the data. Right? It's at 100 Kelvin, the blue system's at 400 Kelvin. They have equal number of particles. These are two systems. I'm going to bring them into thermal contact when I take out the bar. Right? And what's going to happen?
Thermal equilibrium.
Yeah, they're going to move, they're going to bounce around, thermal equilibrium, right? And their temperatures are going to equal out eventually. Now, with only 200 particles in each, that's not a very, in terms of particles, that's not a large number. So you'll see the temperature will fluctuate, it won't steady out nice and flat. If I had a Avogadro, the temperature would work out really nice. Do you know what I mean? Yeah. So you see some fluctuation in the temperature, but you get the idea, right? And so you learned all this stuff in my class in chemistry in high school, thermal equilibrium, temperature, but I want to take this to a higher level today, and then we'll see how it works out. But let's just watch it go. You can see the red and the blue are mixing, right? What's happening? Entropy is increasing, right? Makes sense to everybody? And in that entropy increasing, we're approaching, you can see equilibrium. And like I said, it probably won't steady out perfectly flat because we're only dealing with 200 particles each, right? If we had an Avogadro number, then you would actually get a nice average. But you can see they're fluctuating around, and they started very different. It was 400 and 100, right? And now they're in the 250s range, so we've kind of reached an equilibrium. All right, does that make sense to you guys?
It does.
Okay, let's approach this. Let's reset it. And we'll turn that back on in a minute. Oops. Let's approach this from a more theoretical foundation. So if I have two systems, A and B, okay? And I want to think about the multiplicity. What's the multiplicity again?
How many microstates?
The number of microstates in a macrostate. Right? So we have multiplicity of A and multiplicity of B. You can kind of think of it like a probability. Anybody know what I mean by probability, right? How many states there are, right? You can think of it kind of that configuration. So when I bring these into thermal equilibrium with each other, right, I connect them. So now what happens when I bring them into thermal equilibrium?
Multiplicity is going to be the same.
Okay, well, heat's going to flow, right? and something's going to equal out. So heat's going to flow from here, right? QH, QC, you remember this, don't you?
Yeah.
But I can express QH in terms of the amount of energy lost by A. So I lose the amount of internal energy dA, it comes out, and this gains the amount of internal energy dB. Or a little bit, D is for the infinitesimal, a little bit. So A loses a little bit of energy, B absorbs a little bit of energy, that's the QH and the QC. Right? So if QH plus QC is equal to what? What are those equal to? 0, right? That means dUA plus dUB equals 0. The energy lost by one is equal to the energy absorbed by the other. That's conservation of energy, right? You guys with me? That means the entropy is going to, or the multiplicity is going to change, right? A is going to change, B is going to change because the multiplicity depends on energy. Okay? But let's look at the product. The total multiplicity is just like probability. How do you figure out the probability of one system and another system? You multiply. So the total probability here is going to be the product of A and B. So when I bring these together, I get a new multiplicity function. I had their own multiplicity A, multiplicity B, bring them together. Now we have a total multiplicity, the product of A and B. And these things are going to mix. They're going to exchange energy so that the total multiplicity is going to be maximized. Right? This is going to get a maximum value. Does that make sense, everybody? So. Okay, how do we figure out a maximum? What happens at the maximum?
Is it the same?
Not necessarily the same, no.
The derivative is 0.
The derivative is 0, right? Or a change would be 0. So at this maximum, then any change should be 0. So I'm going to calculate the change d sigma total, right? Any change, a little change in d sigma total, and it's going to depend on what sigma total is, but it's the product of these two, right? Sigma A, sigma B. Well, that's the product rule, right? So that's going to be equal to the partial of sigma A. Where's the eraser? With respect to UA times a little bit of change to UA. So a little bit, right? Oh, and then, so this is the derivative of the first times the second, right? That makes sense, everybody? This is a little change in the first times the second, plus what's the other one? The first times a little change in the second, right? Oh, sigma B. And what does that got to equal? 0, if it's maximized. Right? So what I'm saying is, when I get to the maximum, right, when I bring these together and I get to the maximum value, the change out, right, going from left to right or right to left, any heat exchange isn't going to change the total multiplicity because I'm at the maximum at 0. The changes. Does that make sense? So the deviation, the little change is 0. So this is 0. So now I'm going to take this and I'm going to simplify this, do some algebra. And notice I'm mixing, I got a sigma A and a sigma B and a sigma A. I've mixed A and B, so I'm going to separate them out. I'm going to have one term with all A's, one term with all B's. And I do that by multiplying both sides of this equation by 1 over sigma A, sigma B. If I multiply that through, what do we get? You know, if I multiply by to the first term, what's going to cancel? Sigma B. And so I'll be left with, the first term will read 1 over sigma A times the partial of sigma A with respect to energy A dUA. In the second term, A is going to cancel, so I'm going to have the same thing. 1 over sigma B partial sigma B with respect to UB times dUB equal to 0. So by multiplying by this 1 over each function, I've separated out a left and a right. Or terms. You see what I'm saying? This is a handy trick in physics to do when I want to separate things. Because a lot of times I'll get things out of a product rule and I can separate it this way. Okay, so let's look at that term. So I need to erase. Everybody is interested? Got it? You can erase this? I need room to work. Okay, well, notice UA and DUA and DUB are related by this equation, which tells me what? They equal 0 added, but they're equal and opposite to each other, right? Because when one absorbs, the other gives up. So I can replace DUB with minus DUA. So I can write this as, and then I have DU and A in each term, I can factor it out. So I'm going to be left with 1 over sigma A partial of sigma A with respect to UA minus 1 over sigma B partial sigma B with respect to UB times DUA equals 0. But I just replaced DUB with minus DUA and then factored it out. Now I have two things multiplying each other equal to 0. Right? This quantity here, and inside the brackets, and then DUA. DUA is a change. Well, the change isn't equal to 0, so that means this thing has to be equal to 0. Or this term has to equal that term. Right? So 1 over sigma A partial sigma A with respect to UA equals 1 over sigma B partial sigma B with respect to UB. These are equal. Now, what does that mean? We can simplify this a little bit. If we think about this particular form of combinations of functions and derivative of functions. So if we go back and let's say we take the derivative with respect to x of ln of g of x. Right, what is that? What's the derivative of the ln?
Is it 1 divided by g of x?
Sure. It's going to be 1 over g of x, and then I got to do the derivative of the inside, which is what? The derivative of g with respect to x, right? Now look at this, and look at this. It's the same thing, right? That's g, this is sigma. So I could write this, I have this, I could write it as the derivative of the ln. So I can write this equation as the derivative of the ln of sigma A with respect to UA is equal to the derivative of the ln of sigma B with respect to UB. Right? Ooh, we saw ln of sigma before, didn't we? What was that? Say it out loud, Mary. Entropy. This is what we're saying. So if we define entropy as the Boltzmann constant times the natural log of the multiplicity, I could write this in terms of entropy. That tells me the partial of the entropy A with respect to energy A equals the partial of entropy B with respect to energy B. So what were we setting up at the very beginning here? By setting this equal to, the derivative of this equal to 0, we were doing what?
Finding the maximum.
Finding the maximum, or finding the condition for thermal equilibrium. Right? And thermal equilibrium is reached when the derivative of the entropy with respect to energy is equal for each object, or each system. Okay? So that's our idea of thermal equilibrium. Yes?
So because DUA and DUB are equal, does that mean that the partials are equal?
Yeah, the partials are equal at thermal equilibrium.
No, like just DUA.
Oh, they're equal and opposite.
Yeah. Like, so because it's the partial, it doesn't change the fact that
Right.
it's still equal.
Yeah.
So then wouldn't the entropies have to be equal?
The derivatives have to be, because this is doing the partial derivative.
Okay.
So it's not just the entropy, but the derivative of the entropy. So one can have more, one can have less, but they're changed.
Okay.
Does that make sense?
Yeah, that makes sense.
Oh, what's in the numerator? Is it partial?
Yeah, it's partial.
SA? What's
S
that?
sub A.
Sub
Partial
A?
S sub B.
What's sub A and sub B?
Yeah, so this is entropy of A, entropy of B.
Okay.
Right? So that's how we get our definition of temperature. Because we say thermal equilibrium occurs, they have the same temperature. So that means temperature has to be defined by this partial. So 1 over T equals K, partial of S with respect to U. That's how we define temperature.
Dr. Browning, does it also imply that the multiplicity is going to be the same?
Not the multiplicity, the derivative of the multiplicity. They're going to have different multiplicity. Because imagine you have let's say you had a system with 500 particles and one with 10 particles.
Mm-hmm.
There's no way they're going to have the same multiplicity because you just have way more particles. But the derivative of the multiplicities will be the same.
So like the change in multiplicity.
Yeah, the change. So as you move heat from one to the other, it's the same either way. So that's equalizing. So because you're maximizing this quantity. This is really what's being maximized, is the total multiplicity when I bring things in thermal contact.
So the number of microstates would decrease for one and increase for the other? Or no, they would both increase at the same rate.
Right, they're equalized so that you would get this maximizing, but they're equal and opposite because remember there's a minus sign. Now if I switch from here to here, right? If I move them both with respect to A, it'd be a minus. But yeah, so the total multiplicity is maximized. We can also write this, now that we know this definition here, right, we could write this out. If we go back to this and we take the derivative, right, so if I want to maximize this, sigma total, that's like taking the maximum of sigma A, sigma B, that's what we did, right? But I can write this as K ln of sigma total, which is K ln of sigma A, sigma A, sigma B. Because if I want to maximize, the product, that's also maximizing the log of the product. Right? Because the function, the log function is linearly increasing with the value. Well, not linear, but increasing with the value. So they go together. Right? It doesn't have a minimum difference. So if you maximize the function, you also maximize the log of the function. And log A, log B multiplied is what? Log A plus log B, right? So I'm running out of room here. So we got log of AB, or sigma A, sigma B is log sigma A plus log sigma B. And if you multiply by a K, you get the entropy of A
Plus entropy of B.
plus the entropy of B. So the total entropy is just the sum of the entropies. And we're going to maximize that.
Did we say that entropy could be negative though? Like because you're not factoring in the environment? How would that work?
Yeah, well,
Like if you have two gases and they're mixing, and
Yeah.
one is getting colder. Would
so
it-
the entropy, right, the entropy can change. It could be a negative, it could be positive, yes.
So like the colder, well, no, the colder one would have a positive entropy. then.
Well, they're all gonna have a positive entropy,
But the
because
change,
it's the number of microstates, right?
the
That's
change in
positive.
entropy can go down, right?
Yeah, one can go down, the other can go up. Let's look at that in terms of back at our simulator now. Thinking about this idea of multiplicity, number of states, instead of just thinking about random motion of the molecules. Right, does that make sense? Let's kind of look at it a different way. Now we've done all this beautiful mathematics, which kind of tells us about the universe from a different perspective.
How could that be applied to like real world problems?
What do you mean?
I mean, how does entropy apply to, let's say, the things that we have in the real world? Let's say a car engine,
Yeah.
or
So,
the atmosphere.
how much energy you can get out of a system, like a car engine, is determined by entropy. So all your thermodynamic systems are determined by how can you maximize the entropy of the universe total. So, you only get 20% energy out of gasoline because you got to maximize the entropy. Right?
So if you have more entropy, you're gonna have more efficiency?
Not necessarily. It's kind of like this. Like you learned in biology, chemistry, energy is everything,
Mm-hmm.
right? But what I'm telling you, energy is actually just the bookkeeper. You just got to total up the total energy. Where the energy goes, how the energy is divided between systems, that's determined by entropy. So entropy is kind of the boss. It tells where the energy goes, and conservation of energy just makes sure you only have so much. Does that kind of make sense? Entropy's in charge instead of energy. There's a little different way to see things. I don't know if that makes any difference to you, but it's like, wow. This thing that they barely taught about, entropy, that's the king. That rules the thermodynamic world.
And was it discovered in like 100 years ago?
Yeah, when
Like recently?
after energy was discovered, yeah.
Do you know how they did discover it?
Of entropy?
Yeah.
They were looking at engines and cycles of engines. They found, oh, this is interesting quantity, Q over T. Seems to be important. So they didn't know about it, multiplicity, early on, and that was later. All right, let's do this again. Let's make it really high, 500. It only lets me put 200 particles in each. But thinking about all this, what we talked about, right? So, everything about all this stuff, two gases going, right? Same number of particles. But this one's obviously got more entropy because it has more energy, right? Anybody remember the formula? Do you have it in your notes, somebody?
Which one?
For the multiplicity of a gas, didn't I give it to you?
Oh, the long one?
Yeah, the long one.
I do.
Do you have it written down?
Yeah. I think I have it.
Matthew, you have it written down for me?
I have it for.
It was a long formula.
I have for the isothermal and isobaric.
No. The entropy of an ideal gas. It was a big long formula.
Oh no.
Do you have it written down? Otherwise, I'll look it up.
I know what
You didn't write it down probably because you didn't need it.
Yeah. That's correct.
Was it NRLN?
No.
No.
That was
I'll just
It's
pull it
a
up real
really,
quick.
really long one.
I'll pull it up. It's easy to find. It's on hyperphysics. That one. That nasty thing.
Oh no.
S equals NK ln V over N 4 pi U, that's internal energy, 3N H squared, 3 halves, plus. Okay, so we have two gases, each with a total, this is their entropy, right? They have the same number of particles, I made sure of that. They have the same volume, right? That's the same between them. What's different is the internal energy. One's got more than the other, right? So U's different. Does that make sense? So each has their own internal energy. Now what's going to happen when I open the thing? They're going to mix, but think about it in terms of multiplicity and entropy. Right? Let's talk about in terms of entropy, right? When I open the thing, this one's going to lose entropy, this one's going to gain entropy. Right? And when is that going to stop? When the entropy, the total entropy is maximized. Which means what in terms of multiplicity? Right? The multiplicity will be maximized. Right? So again, the number of microstates here for this macrostate is a lot more than the number of microstates here for this, right? Because it has more energy. But when I bring them together, bring them in thermal equilibrium, I'm going to exchange energy between the two systems, and I'm going to get to a point where I've got the most microstates for that macro. I've gone to the configuration with the most microstates. Right? I maximized the multiplicity. Okay? So here it goes. This stuff applies to all systems, whether it's a gas, a solid, chemical reactions. All of it can be explained in terms of maximizing the multiplicity. Yes, Mary?
Why do like the blue particles expand more than the red particles?
Because they have higher velocity, so they're going to travel faster to begin with. Eventually, it'll equal out.
Yeah.
Question?
Can you explain the data?
Oh yeah, I forgot to turn on the data. Thank you. Yeah, it started at 500 and 100. Right? You can see this one's still quite a bit hotter than that one. Well, now they're pretty equal. So they're finally getting down to around 300. Right? And you can see we're getting. And all thermodynamics can be explained in this. Right? This is a powerful concept.
Do molecules really bounce like that?
In the ideal gas model, now we didn't allow chemical reactions to happen, but you could, and you would find the multiplicity would still would increase. But we didn't include that in here. Question, Mary?
No, but like in reality, like does that actually happen?
Oh, this?
It's like not-
Yeah, if you had, hydrogen gas, not hydrogen, helium gas and neon gas are both noble gases, monatomic.
They would just kind of float around.
Yeah, this would be a very good description of their behavior. They're probably your closest you're going to get to an ideal gas. When I learned, I was just amazed. Like, here's the stuff I learned in high school and biology and chemistry about temperature, but they never said what temperature really was. And entropy was a mysterious concept saying disorder. But here, it's just multiplicity. Everything's just multiplicity, and you're working out maximizing the multiplicity. That's what's going on in thermodynamics. So I think it's amazing. Any questions?
I want to understand it, but I don't.
Right. You want to know more now, though, right?
I just want to get it.
That's why you got to take thermophysics, thermodynamics, and statistical mechanics, because we'll cover all this in great detail.
Are you gonna offer that next semester?
Not yet. So.
Probably next one?
Huh?
Dr. Browning says we're not ready for it, and I think if Dr. Browning says we're ready for it, we're not
I would say
ready
you're
for
probably
it.
not quite ready for it,
I don't think we're ready for physics 2.
because we do a lot of infinite sums, and partial derivatives, and some crazy integrals. Because it's very mathematical.
Do you think spring 26?
We'll see. We're going to offer classical mechanics in the fall, so you all should take
Oh, in the
that.
fall?
It's a physics class.
Oh, I'm gonna take
Are
that.
you teaching that?
Yes. I'm teaching that.
Classical mechanics.
So it's like physics 1, but more advanced.
Oh my gosh.
What is it?
This is.
What do you mean?
And that's physics 1 but more advanced. What is it?
This is physics 2.
And then thermodynamics.
But thermodynamics is like the first half of physics 2, more advanced. And then E&M is the second half of physics 2, more advanced.
Now we're gonna get into electrical, right?
Yeah, we're getting electrical. Electricity, magnetism, circuits.
E&M.
Have you started on a test?
No, I'm going to this one.
Okay.
And I'm going to go see a movie, I hope.
There you go. Marvel.
The new Marvel movie!
Marvel. I was talking
Is
about
it
that all the
today?
time.
Okay.
You guys watch the Marvel review?
You know what? We got time. Let's find a preview.
Thank you for doing that.
I did just.
From the bottom of my heart, Dr. Browning, thank you for giving us a chill day today.
Yeah.
It's Iron Man. You're welcome.
What was
Sometimes
it?
you need it after a test.
It's Iron Man.
True.
Oh, it's not Iron
No, it's
Man.
Captain America.
Captain America.
Yeah.
Oh,
But I mean,
yeah.
it's with Captain fucking.
Yeah, it's the.
Brave New World.
Yeah.
That's in the book.
And it's got Harrison Ford.
Ooh.
Oh my
I
gosh.
love him as an actor. I hear he's a diva though.
You asked for me. Here I am.
Come on, and he's a great actor. We gotta play this
You
Falcon.
wanna help me? Is there anything you remember?
Ladies and gentlemen, the President of the United States, Thaddeus Ross.
Whatever this is, Camp, be careful.
He's like 80 something. Harrison.
Yeah, he's old.
And he's still
What
acting.
do we know?
There were 5 shooters. This was a coordinated terrorist attack, sir.
I was a wartime general. Now I'm a wartime president. Your inner circle's been compromised. Let me fix it. Watch yourself. You're not Steve Rogers. Right. I'm not.
Oh.
Wait for it.
Yeah, it's physics right there.
We're on the brink of war. I can't trust anyone.
They always do the physics bad and do shit.
Nothing about this feels right.
Captain America. You ever ask yourself, who's playing who?
Someone's been pulling the strings on everything. You're under arrest? I don't want a variable out there that I can't control. Captain America caught without his wings.
You like to play dress up and blindly execute the state's orders.
Don't say I didn't warn you.
What if this is a trap? You don't need to know what this is.
Red Hawk.
Harrison Ford?
That's crazy.
You want me? Come and get me!
The physics is all bad in there, but that's okay.
When he fell, like, all that gun shit was crushing.
Or when he jumped through the car.
It's
Oh,
Bucky.
man, it's so big.
Anyway.
Drive through Oklahoma.
Okay, I'll see you guys in lab. We'll let you go a little early.